In the previous chapter, we covered the fundamentals of how an emulator works, focusing on the most essential aspect of any emulator project, the cycle counting. You can find a clear example of this concept in the Atari System Emulator, a project I created so you can dive into the code and easily explore the inner workings of emulation. My priority here was to keep the code simple and readable, rather than focusing on high-precision accuracy. You can download the emulator using the link in the description. Also, if you haven't seen the previous video yet, I highly recommend checking it out first. It will help you better understand the concepts we're about to dive into in this second part. Early personal computers and consoles, such as the Commodore 64 or the Atari ST, relied on numerous tricks to squeeze every bit of performance out of their limited resources. In some cases, programmers even exploited hardware quirks and design flaws to their advantage, displaying pixels in the screen borders, creating complex visual effects, or multiplying the number of on-screen sprites. To successfully recreate these tricks, we must emulate every single hardware component as accurately as possible. This is known as Low-Level Emulation or LLE. As we saw in the previous chapter, it's not just about the CPU's cycle counting. It requires cycle-accurate emulation across the entire system. This means achieving perfect synchronization between the CPU and specialized chips, like the VIC-2 in the Commodore 64 or the shifter in the Atari ST, to ensure every scan line and every pixel is rendered exactly as it would be on original hardware. CPUs, like the Motorola 68K, are relatively straightforward to emulate at a low level. Most emulators rely on opcode dispatch tables with specific functions for every instruction. To give you a simplified example, let's imagine that we maintain a variable for the program counter, or PC, which tracks the current execution point in the emulated memory. We read opcodes by using this counter, and if the opcode we find in memory is, for instance, a move instruction, we execute a function that moves the value following the opcode to the address, stored in register A0. We then advance the PC 4 positions and update the cycle count for that instruction, which in this case would be 12. By having a function for every Motorola opcode, we can precisely track the cycles consumed by each operation. In many cases, simply tracking CPU cycles isn't enough. It's also vital to account for the cycles consumed by every other hardware component. This is essential for emulating a Super Nintendo or a Commodore Amiga. To recreate that system accurately, we must keep the CPU cycles perfectly synchronized, for example with the Agnus chip. It is crucial to calculate the exact number of cycles the Blitter or Agnus requires to complete their tasks. This level of precision is the only way to correctly emulate the advanced graphical effects used in games and demos, where the timing between the CPU's instructions and the custom chip's operations must be frame perfect. The previous method is ideal for emulating systems where cycle-accurate precision is paramount, but it isn't fast enough to emulate more complex or modern hardware. In these cases, it's better to sacrifice precision for performance by using just-in-time compilation, or JIT. With this system, instead of using a function to interpret each CPU opcode individually, the JIT compiler translates them into native machine code for the host processor. This achieves near-native performance, although it requires an initial warm-up period. You've probably noticed that some emulators experience stuttering, especially after a loading screen. This happens because the JIT is actively analyzing and compiling code blocks in the background. However, once the system processes enough batches and the cache achieves a high hit rate, it reaches a steady state, and execution becomes significantly smoother. This compilation isn't limited to the CPU. It also occurs at the GPU level. In these cases, the emulator takes the original shaders and translates them into machine code that the host computer's specific hardware can understand, utilizing modern APIs such as Vulkan, OpenGL, or DirectX. In the next chapter, we'll see how emulators go beyond simple translation, enhancing visual quality by increasing the internal resolution and employing various upscaling techniques. As we saw in the previous video, emulators handle every read and write the emulated CPU performs through specific pieces of code. These routines catch those requests and recreate exactly what the original hardware would have done. Let's look at an example. On the Commodore 64, writing a value to D020 changes the border color, while writing to D021 updates the background color. These aren't just normal memory locations, they're mapped to color registers inside the VIC-2 chip. Our emulator should respond to those writes, just like the real machine did. Now that we've seen that example, let's think about emulating the video processor of a console or computer, where polygon rendering is handled separately from the CPU, like in the case of the original PlayStation or the Nintendo 64. In these systems, we may not need the same level of cycle-by-cycle precision in the main processor to display graphics, since on the original hardware that work is handled by a dedicated graphics chip. This is where a different approach comes into play: high-level emulation, or HLE. Instead of recreating every hardware component down to the smallest detail, the high-level emulation focuses on reproducing the results of the original system's operations, rather than the exact way they were carried out. Rather than simulating each instruction and every internal timing interaction, the emulator identifies higher-level functions, such as graphics commands or audio routines, and replaces them with equivalent functions on the host system. In other words, instead of mimicking the hardware step by step, the emulator translates its intentions. For example, if a game sends a command to draw a textured polygon, an HLE emulator doesn't necessarily simulate the internal workings of the original graphics chip. Instead, it interprets that command and asks the host GPU, through a modern API like Vulkan or OpenGL, to render an equivalent polygon directly. This approach sacrifices some hardware-level accuracy, but in return it can achieve much higher performance and even allow visual enhancements that weren't possible on the original machine. Older computers and consoles work directly with pixels, and emulators can stretch them or apply shaders to smooth them out, but the results are usually limited. With vertices, however, things are different, since 3D systems define their graphics using geometric data. It's possible to recalculate vertex positions for modern resolutions, allowing games to be rendered much more cleanly than on the original hardware. All the ideas we've explored in this video don't apply only to emulation. There are other types of software that use these same concepts, not to emulate a system, but to translate calls between different platforms. You might be familiar with Proton or Wine. They aren't emulators, but they rely on a similar approach to the one we've discussed here. The difference is that instead of recreating hardware, they translate system and graphics API calls from one operating system into another. Wine's call translation is more straightforward when both systems share the same architecture. If a program says "open a window," Wine simply translates that into the host system's own "open a window" instruction, with very little overhead since no hardware emulation is involved. In a similar way, when Dolphin processes a Nintendo GameCube game and encounters a command like "draw a triangle," it translates that instruction into an equivalent "draw a triangle" call using modern graphics API such as DirectX or Vulkan. This scenario changes when we're dealing with different architectures, such as a Mac Silicon running Windows programs or games built for x86. In that case, as we discussed in the previous chapter, the CPU instructions also need to be translated, typically through just-in-time or ahead-of-time recompilation. Even then, this still isn't traditional hardware emulation. It's closer to what a high-level PlayStation 3 emulator might do: recompile the original code for the host architecture while translating the graphics commands to modern APIs. There are also projects that aim to bring games from older platforms to modern systems by transforming their original code. For example, Unleashed Recompiled converts Sonic Unleashed from Xbox into a native version for Windows or Linux, or N64 Recompiled, which takes the original game binaries and turns them into code that can be compiled for modern platforms. These projects don't approach the original software from an emulation perspective, which makes them particularly interesting. Instead of simulating the original hardware, they adapt and modernize the original code so it can run natively on today's systems. Finally, we can't forget to mention hardware implementations based on FPGA. FPGA are not emulators. They recreate the original machines at the hardware level by replicating their logical gate structures. Because this operates at such a low level, it can potentially offer the highest degree of accuracy compared to the original system. However, this depends heavily on how faithfully each hardware component has been reproduced. In some cases, especially with proprietary or poorly documented chips, developers have had to rely on reverse engineering due to the lack of official documentation. I won't go into detail about these systems in this video, since we've already covered them in depth with two excellent examples, the MR project and the new Commodore 64 Ultimate. If you missed those videos, be sure to check them out. You'll find the links in the description. Across these two videos, we've taken a look at how emulators work. There's still plenty more we could explore, but I hope this overview has given you a clearer and more interesting perspective on what's happening behind the scenes. If you'd like me to dive deeper into any of the concepts we've covered, let me know in the comments. And if you haven't watched the first part yet, I encourage you to check it out. You'll find the link in the description. Finally, let me remind you that the Atari System emulator is available for you to explore. It's an Atari ST emulator I created using simplified and easy-to-follow code, so you can see in a more practical way how an emulator works. I've made a few improvements since the previous video, and I'm planning to add more updates soon. You'll find the download link in the description. I hope you found this video interesting, and thank you very much for watching all the way to the end. If you enjoyed it, please give it a like. It really helps the video reach more people and supports the growth of the channel. And don't forget to subscribe. See you soon.